Hello, I am 3STEM. This is lesson 10E, and we're calling it Find Partial Sums of Telescoping Series. Now, the reason why we call it a telescoping series is that we're acting in the solving of this like a telescope. So you pull out a telescope and you expand it and you put it up to your eye to see things that are way far away. And then when you're done with the telescope, you can compress it down to something that is a nice compact portable tube when you're through. So these problems take expanding the problem to look for a pattern, and once you see what's going on, then you compress the series down to a compact solution. Do you remember doing partial fraction decompositions? We'll only do the simplest of those kinds of problems, but we will do them. And so let's start by having you do one to remind you. Here's a problem here where I have an expression a sub n is equal to 3 divided by the product 3n minus 2 times 3n plus 1. And you can actually take that and you can break it up into a over 3n minus 2 plus b over 3n plus 1 by doing partial fraction decomposition. So I'll give you a try right now. Give it a go, and I'm going to pause the video, and when we come back, I'll work out the problem for you, and let's compare notes. So if you remember now, in solving partial fractions, one of the steps was to take that denominator and multiply it by both sides of this equation. So that's going to look like this when we do it. So when we do that too, you'll see that this cancels the denominator and we just end up with a 3 on the left-hand side. But as we do the right, as we multiply these things, you end up with a times 3n minus 2 times 3n plus 1, but the 3n minus 2 cancels, and so that just ends up being a times 3n plus 1 plus, and the same goes for b, the 3n plus 1 cancels, and so we end up with b times 3n minus 2. Now, to solve for a and b, it's just a matter of finding the values of n that make that work. And so the easiest thing to do is to make the phrase like 3n plus 1 equals 0 so that we can solve for b, and I'll show you how that's done. So 3n plus 1 is equal to 0 when what value of n? So that's going to be when n is equal to negative 1 over 3. So let's just go ahead and let n be negative 1 over 3. And we know that that already takes care of the a. That turns it into 0. And so we end up with an expression that looks like this. 3 is equal to then b times, and we said n is equal to negative 1 over 3. And so that ends up being negative 1 minus 2. That's a negative 3. So b then ends up being negative 1. So let's go the other way now. Let's let 3n minus 2 equals 0. And that happens when n is equal to positive 2 over 3. So now if we let that happen, we know that that's going to turn the b expression into 0. And the a expression then is going to be times 3 times, that's going to be 2 plus 1. That's a times 3 is equal to 3. So that turns a into positive 1. So what that does for us now is allows us to say that this expression can be rewritten as a sum of two fractions. And those fractions look like this now. 1 over 3n minus 2 plus negative 1 over 3n plus 1. And as we move that forward now, we're actually looking at this guy right here called, we're finding the partial sums of telescoping series. This expression here is you're given 4 terms of a series that's going on to infinity. So just let's look at them term at a time. 3 over 1 times 4 plus 3 over 4 times 7 plus 3 over 7 times 10 plus 3 over 10 times 13, and on and on and on. So something that you want to see is that we look closer enough like this. If you look at just the products down below, 4 minus 1 is 3, 7 minus 4 is 3, 10 minus 7, 3, 13 minus 10, that's 3. So those are some things to be looking for. And also what you're looking at too is the fact that you've got that 3 there is a part of every term. And that really, when you think about it, can be factored out. So let's look at the first factor of the other parts here. This 1, this 4, this 7, and this 10. And what I want you to be thinking about is to recognize that that's 1, 4, 7, 10 is an arithmetic series with a common difference of 3. So couldn't we write it this way? 1, which is the first one, plus 3, the common difference, times n minus 1. And we have to kind of solve this out, so we're going to just go 3n minus 3 plus 1 is 3n minus 2. And the 4, 7, etc., we'll call that 4, 7, 10, and 13. That's also an arithmetic series, starting with 4 and having a common difference of 3. So let's write that one down. We've got 4 plus 3 times n minus 1. And that becomes 3n minus 3. 4 minus 3 is 1, so this becomes 3n plus 1. So we can rewrite this expression now as the a sub nth term is going to look like this. It's going to start with a 3 on top, and it's going to have 3n minus 2 times 3n plus 1. And there's our a sub nth term. So going further then, we can actually go, then our sigma notation is going to look like this, that n is equal to 1 for the first term, moving all the way out to infinity, and it's going to just be. So there's that. But we want to turn this into a partial fraction and find the sum of that partial fraction. So in order to do that, aren't we going to look at it this way, that we actually want to now change the index to something not n, but maybe let's call it j. So j equals 1, and we're going all the way to n because we're going to find the first n terms. And we're going to say that that's now 3 over 3j minus 2 times 3j plus 1. And that's what that looks like. But wouldn't it be nice if we could break that fraction up at the bottom? And we can, because we're doing this. 3 over 3j minus 2 times 3j plus 1. Well, that's the problem that we just did up here. There, see, 3n minus 2, 3n plus 1. And we figured out that that was 1 over 3n minus 2 plus negative 1, which you can actually just call that minus then, 1 over 3n plus 1. So we're just going to go ahead and write that. So this is going to be 1 over 3j minus 2 and minus 1 over 3j plus 1. So if we're going to write this expression here, we can actually write that expanded now according to the properties of sums. So we can say, and we're not going to make it two separate sums, we're just going to make it a difference inside the one sum so that it looks like this. So that's our summation expression. And now we go on to the telescoping part, and watch what I do as I do this. We're going to look at maybe 3. Let's do 3 versions of j. J equals 1, j equals 2, and j equals 3. So in each case, I'm just going to label it over here, j equals 1. When j equals 1, then we're just looking at this expression right here. 1 over 3 times 1 minus 2. Well, that's 3 minus 2, and that's just 1. So, but I'm going to write it this way. And the reason why is because I want to make sure that I see everything in a particular way and not reduce things too quickly, because it starts to cloud what we're really looking at. Minus 1 over 3 times 1 plus 1. Well, 3 plus 1 is 4, so it's just going to be 1 over 4. There's our first term. Now, when j is equal to 2, we have this expression. 1 over 3 times 2 is 6, minus 2 is 4. Minus, and then the second term becomes 1 over 6 plus 1 is 7. And then let's go for the third term. 3 times 3, 9, minus 2 is 7. So this becomes 1 over 7 minus 1 over 9 plus 1 is 10. So here's what I'm wanting you to see, is that actually we're looking at this and we're saying that this looks this way. This is this term plus this term plus this term plus on and on and on. And here's the thing that I'm wanting you to notice, that if I look at that 1/4 now, this is minus 1/4 and this is plus 1/4. Well, that just becomes 0 when I combine them. And this is minus 1/7 and this is plus 1/7. Well, that becomes 0 as well. And notice then that that just keeps on going. We keep on doing that. And as we get out to now the nth term when j is equal to n, well, that's just going to be 1 over 3n minus 2 minus 1 over 3n plus 1. Well, something that we're interested in is what happened in front of j is equal to n. Well, wasn't that n minus 1? So let's just look at that. And let's actually do some fixing before we actually write these out. So we end up with 1 over 3n minus 5. And the next one becomes 3n minus 1 times, or plus 1. Now, that happened before n. So if we continue writing then this plus, we end up with this expression plus this expression. And so look at what happens here. This 3n minus 2 expression is taken away from that one. And so we know that this one was taken away from something in front of it. And here's what we get to observe now, that our sum is actually equal to then, and I'm just going to label our sum s sub n now, is equal to this 1 right here, and everything else got eliminated, minus 1 over 3n plus 1. And we can do the math on that. We just go 3n plus 1 over 3n plus 1 minus 1 over 3n plus 1. And finally, that becomes 3n over 3n plus 1. And that is the sum of our telescoped equation. So here in example 2, we are looking at a series that's similar but different. And how it's different is that now we're just looking at numbers. We're looking at 1 over 8 plus 1 over 15 plus 1 over 24 plus 1 over 35 and on and on and on. But how's that growing? We're going to have to be thinking about that for a second. And one way to look at it is maybe to look at it from finite differences. So let's just see if we get anywhere with finite difference. We know that those denominators do not make an arithmetic series, and you'll see why here. Let's just go ahead and look at the differences. So 8 and 15, and 24 and 35. Let's see, 8 and 15, that has a difference of 7. 24 and 15, that has a difference of 9. And 35 and 24, that has a difference of 11. Well, hey, look at that. 7, 9, 11. 9 and 7 have a difference of 2, and 11 and 9 have a difference of 2. So I think we can safely say that this is quadratic that's occurring in the denominators of each term here. And so how do we figure that out? Well, we can look at this and say, okay, how about this? This is going to be 2 times 4, and that's the denominator, remember, so we can put the 1 up there. And plus, let's go for, well, I see a 3 in there. Let's say 3 times 5. Well, I just went up from 2 to 3, and I went from 4 to 5. This is pretty cool. So how about this? How about the next one being 4 times 6? And notice, too, that 2 and 4, that there's a difference of 2. 3 and 5, there's a difference of 2. And 4 and 6, there's a difference of 2. So I think we got something here. So I think we can safely say then the next one is going to be for 5 times 7. 5 times 7, and 7 minus 5 is 2. And I think that we can just get bold here and say then the next one for sure is going to be 1 over 4, 5, 6 times 8, right? And I think we've got it. So that's moving on and on and on, and we can figure out how that's going. Well, let's look at each piece of that and say 2, 3, 4, 5, 6. That's an arithmetic series with a difference of 1. The first term is 2, so we can just calculate that by saying 2 plus 1 times n minus 1. That's n plus 1. And so that's the phrase for the first part. The second part starts with a 4, so we say 4 plus n minus 1, which just becomes n plus 3. And so there we have it. I think what we have then is each term is made up of n plus 1 times n plus 3. And let's just kind of check it, shall we? That's our a sub n term. Let's say what happens when n is 1. 1 plus 1 is 2. 1 plus 3 is 4. 2 times 4 is 8. So the first term is 1/8. Let's go for 2. 2 plus 1 is 3. 2 plus 3 is 5. 3 times 5 is 15. So that second term is 1 over 15. And I think we have it. So there's our a sub nth term. So now what we want to do is use that a sub nth term and create a sigma notation representing the sequence as we see it, the series as we see it. So let's do it this way. We're going to stay with the index of n for now and say we're going to infinity. And so we can actually say that that's 1 over n plus 1 times n plus 3. And that's for the infinite series, going all the way to, if we wanted to just keep on saying and on and on and on. But let's take a look at, if we're talking about the first n finite series, a finite series of n terms, then what we want to do then is change our sigma to look like this now. We're going to use a different index, not n, so let's call that j. We're going to say j is equal to 1, and we're going up as high as n because we're going to stop at the nth term. And that's going to be 1 over j plus 1 times j plus 3. But it's going to be difficult to write this out. It's actually easier if we could break up those two fractions down below, and we already remembered how to do that. And so we're going to actually do this. We're going to say 1 over j plus 1 times j plus 3. And we're going to turn that into partial fractions. A over the first one, j plus 1, plus b over j plus 3. And so there we have it. We're going to figure that out. So that's going to take multiplying both sides by j plus 1 times j plus 3. That's going to cancel this, and that just turns that into a 1. down here, and we have a times j plus 3 plus b times j plus 1. Well, what makes that first term 3 or 0 when j is equal to negative 3? And let's just go ahead and solve. So j is equal to negative 3, so negative 3 plus 1 is negative 2. Negative 2b is equal to 1. That means that b then is equal to negative 1/2. And so that's one case. Another case is going to be when j is equal to negative 1. And that's going to turn the b term into 0, but negative 1 plus 3 is 2, so I get 2a is equal to 1. And so that means that a is equal to positive 1/2. Okay, we're going to use that information now, and that means then that we're looking at something that looks like this. We're going to take this phrase and replace the a and the b, and now what we have then is to say that this term becomes 1 over 2j plus 1 minus 1 over 2j plus 3. So we're going to take that. And what we want to do is actually take this expression then and start to look at a few versions of the of what we get. So we're going to say this. Let's let j equal 1 and start taking a look at what we get here. So when j is equal to 1, I get 1 over 2 times 2, so which is just 1/4. And then minus 1 over 1 plus 3 is 4, so 2 times 4 is 8. And then we have j equals 2, and let's look at that. So 2 plus 1 is 3, times 2 is 1 over 6, minus 1 over 2 plus 3 is 5, times 2 is 10. Okay, I'm not seeing anything just yet. Let's just keep on going here. J is equal to 3. I can see when j is equal to 3, j plus 1 is 4, and that times 2 is 1 over 8. Minus, and then when j is equal to 3, 3 plus 3 is 6, times 2 is 12. 1 over 12. Let's keep going a little bit more. J equals 4. So when j is equal to 4, now we've got 4 plus 1 is 5, and that times 2 is 1 over 10. Okay, I think I'm starting to see some things. And then j is equal to 4 plus 3 is 7, times 2 is 1 over 14. Okay, so maybe you see what I see, but let's also go to the nth term, and we're going to say j equals n. And so when j equals n, we're talking about 1 over 2 times n plus 1 minus 1 over 2 times n plus 3. And that's our nth term, but we also are interested in maybe taking a look at not just one more, but maybe two more n terms. And so let's terms with n in it. And so let's just kind of calculate some of those. If we look at the first part and say we're talking about j is equal to n minus 1, then that becomes 1 over 2 times just n, doesn't it? And then minus 1 over 2 times n plus 2. So that's how that looks. And then j equals n minus 2. Well, so now we're just going to be going, all right, this is 1 over 2 times n minus 1. And this one's going to become 1 over 2 times n plus 1. Let's see what we got here. So as we look at the n's, here's something interesting. Do you see that this part takes care of this part? So it takes a few terms in order to see that things are being taken care of here. And so that's kind of what I wanted you to see. If we went a little bit further, you'll start to see that, okay, that means then that the first terms are taken care of by third terms back. And I think that we know that that's the case. And here's kind of the confirmation of that this 8 has to go 2 terms, and then it gets rid of that. And this 10th, 2 terms down, and we got that guy. And we know that this 1/12 is going to get something, and that this 1/14 is going to get something. But we didn't quite get rid of that 1/4 and the 1/6. And then we also didn't get rid of that last term down there, and those last 2 parts. And so this is what this is going to look like. As we're adding that all together, we are coming to realize that our S sub n then has in it 1/4 plus 1/6 minus 1 over 2 times n plus 2 minus 1 over 2 times n plus 3. And that's going to be the sum of the first n terms of our series. So this just becomes now a matter of finding the lowest common denominator. So I hope that you see that our lowest common denominator actually becomes 12 n plus 2 times n plus 3. So that's what we're going after. And so each term needs to have top and bottom multiplied by something in order to get that common denominator to work. So we're going to write the common denominator down here. That's going to take multiplying the top of the first one by 3n plus 2 times n plus 3. And the next one is going to take multiplying by 2 n plus 2 times n plus 3. Okay, the next one has 2, we need 12, so we need to multiply by 6. It's 2, but we need an n plus 3. And then that last one is going to take a 6 and the n plus 2. And there we go. So now it's a matter of just cleaning that up. So I think what I'm going to do is just do it. Just about there. And then we've got 5n plus 13 times n all over 12 times n plus 2, n plus 3. And I think we have it. That's our sum of the first n terms of that numeric series that you saw. Now, as we get into talking about example 3, you notice here that we have a sigma notation expression already that's just ready to be broken up by partial fraction decomposition. So we're going to go ahead and just grab a copy of it right here, and we're going to put that copy over here, and we're going to say equals, and we know that there are 3 factors in the denominator, so we're going to say the first part is a over 2k minus 1 plus b over 2k plus 1, and then plus c over 2k plus 3. Now, what I'd like you to do is maybe give this a try yourself, and then I'll just show you what you should be expecting to get. So go ahead and hit pause and give it a try. Now, as we work these out, really what you should be doing is just going after making the 2k plus 1 or the 2k plus 3 or the 2k minus 1 phrases equal to 0, because watch what happens when we do that. We're going to start off by letting 2k plus 1 equals 0. Now, we know that that happens when k is equal to negative 1/2. And so we're just going to go ahead and take a look at that. Well, look at this. If that turns 2k plus 1 into 0, then here we have 2k plus 1 and 2k plus 1 here. So a and c go away, and we end up with 2k, but k is negative 1/2. So we just call that negative 1 is equal to b. Negative 1 minus 1 is negative 2, and negative 1 plus 3 is 2. So we just end up with b times negative 4. And that gives me b then is solved, because that's just going to be positive 1/4, because negative over negative is positive. And then in the next case, we're going to be looking for 2k minus 1 is equal to 0. Well, that's going to happen when k is equal to positive 1/2. So that'll turn 2k minus 1 into 0. So that takes care of b, and that also takes care of c, and those go away, and we just end up with positive 1, because 2k when k is a half is just 1 on the left, and that's going to equal a times 1 plus 1, which is 2. And the 2k plus 3 turns into 1 plus 3, and that's 4. So this ends up being a times 8 is equal to 1, and so a is equal to 1 over 8. And then we're going to say 2k plus 3 is equal to 0. And if 2k plus 3 is equal to 0, then that's going to take k equaling negative 3 over 2. And when we have negative 3k over 2, we've got we've got k is equal to negative 3 over 2. That's going to 0 the a, and it's going to 0 the b, and we're just left with the c. So we have now negative 3 is going to be the 2 times k, because there's negative 3 over 2 times 2, and that just leaves a negative 3. And that's going to equal now our c phrase. So c is going to be negative 3 minus 1, which is negative 4, and negative 3 plus 1, which is negative 2. So we ended up with times c. And so c then is equal to negative, because the negative times negative is positive, and so we end up with negative over positive. And that's negative 3/8. So c is equal to negative 3/8. So there we have it. So we can actually rewrite this now, this phrase. And so we're just going to put it down here. And we're going to replace a with what it is. It's actually 1/8. And with b, notice b is 1/4. But we're going to do a trick here. And the trick is going to be this. We're going to replace b with 2/8. How's that? 2 over 8 is 1/4. But you'll see the reason why we do that. And then c, we already know, is negative 3 over 8. So it's negative 3, and we have now over 8. Okay, so that's what we look like now. So look at what this is going to turn us into. We can actually, as we're looking at that summation, this whole phrase here has that summation in front of it. And so we can actually write it this way now. We're going to write 1 over 8 and grab that summation and know that that's equal to, we're just going to write all these in here now. 1 over 2k minus 1 plus 2 over 2k plus 1 minus 3 over 2k plus 3. And so now that makes that really nice and neat. Now, if we try to evaluate this now, it's going to look like this. Let's just start evaluating. We're going to go k equals 1. I'm going to need about 4 of these. I'm going to go k equals 2, k equals 3, and k equals 4. So let's start with that. So the first one, we're going to let k equals 1. So 1 over 2 times 1, which is 2. 2 minus 1 is 1. So that first phrase is just going to be like this, 1 over 1. And I think you saw me do that before, so we're just going to leave that as it is and not even call that 1, because we're looking for a pattern. And then we're going to take 2 over 2 plus 1 is 2 over 3. And then that's minus 3 over 2 plus 3, which is 5. So 3 over 5. Okay, so keep an eye on that. The next one is going to be when k is equal to 2. So now we've got 1 over 4 minus 1, which is 3. So that's 1 over 3. And plus 2 over 4 plus 1, which is 5, minus 3 over 4 plus 3 is 7. And when k is equal to 3, we're going to have 1 over 5 plus 2 over 7 minus 3 over 9. And then finally, when k is equal to 4, we're going to end up with 1 over 7 plus 2 over 9 minus 3 over 11. Okay, that gives us some clues here. And what we're going to do is that since we did 4 down, we're going to do 4 up from k equals 1. So I'm going to go ahead and just do k equals n. And so what I'm going to do here is I'm going to write k equals n. And so k equals n is just simply this, 1 over 2k, 2n minus 1 plus 2 over 2n plus 1 minus 3 over 2n plus 3. And then I'm just going to go ahead and give you these. N minus 1, and we're going to let k equal n minus 2, and we're going to let k equal n minus 3. And we're going to fill those in, okay? And so there we have it. And this is what I want you to notice. So let's start off with the last part of the triple in k equals 1. Notice there's a negative 3 over 5. And that negative 3 over 5 is going to deal with 2 over 5 from the middle of the next term and 1 over 5. So notice I have 1 over 5 plus 2 over 5 minus 3 over 5. That just becomes 0. And then notice again, negative 3 over 7 takes care of 2 over 7 plus 1 over 7. And 3/9 is going to take care of 2/9 and whatever's beyond that. And so we know that this is going to be taken care of. And everything beyond the 2/3 of the K1 line is going to go away. You can see that. And so we can just go ahead and count on that happening. And then you can see that it happens when we have K is equal to n minus 3, n minus 2, n minus 1, and when K is equal to n. So that the 3 over 2n minus 3 takes care of the 2n minus 3, 2 over 2n minus 3 plus 1 over 2n minus 3. And you can see that trend happening. And so we know that when we let everything go that we know is going to go away, what we have left now is this this negative 3 over 2n plus 1, this 2 over 2n plus 1, and this negative 3 over 2n plus 3. And that's what we're going to deal with now. So watch what we have left. We actually have 1 plus 2/3 plus 1/3, because we have these guys up here. And down below, we have minus 3 over 2n plus 1 plus 2 over 2n plus 1 minus 3 over 2n plus 3. Now this takes some cleaning up. Notice the 2/3 and 1/3, that adds to 1. So 1 plus 1 is 2. Minus, we've got negative 3 plus 2 over 2n plus 1. So that's just negative 1 over 2n plus 1. And minus 3 over 2n plus 3. Okay, we know that our LCD is 2n plus 1 times 2n plus 3. And so this just ends up being then 2 times 2n plus 1 times 2n plus 3 minus 1 times 2n plus 3 minus 3 times 2n plus 1. And that's all over, by the way, our common denominator. So then that becomes 2 times 4n squared plus 8n plus 3 minus 2n minus 3 minus 6n minus 3 all over 2n plus 1 times 2n plus 3. So further cleaning gets me down to 8n squared plus 8n, and everything else just goes away, and we're over 2n plus 1 times 2n plus 3. And that, remember, has this sigma in front of it. And we're going to put it right there, and watch what happens. 8 cancels with this 8 and this 8 up here, so that just all factors out. And what we are left with now is our sigma to n plus 1 times 2n plus 3. And you could further take that and factor out an n. You could call that n times n plus 1 over 2n plus 1 times 2n plus 3. And there you have it. You're going to be having some homework problems that look like this, and you're going to have to kind of telescope out and telescope out even more before you condense your telescope back to its compact form and finally end up with this final phrase of S of n is equal to n times n plus 1 over 2n plus 1 times 2n plus 3. And there's our answer right there. You might want to just watch this video a few times through, follow it along, try to keep up with it, and actually come up with the same answer. So I'm anticipating that I will be seeing many of you in study hall asking questions. I had to work really hard to get through all of the problems and figure all of them out, but I have them all. And so come to study hall, ask me questions, and I think that this one is really interesting. I find problems like these like puzzles, and so it's almost having fun doing some of this stuff. So good luck, do your homework, and we'll see you next time.